Today we're going to look at probability and combinations. The probability of an event E is the number of ways the event can occur divided by the number of elements in the sample space, or the number of total possible outcomes. Now, n of E and n of S can be found sometimes by counting permutations. In some of the examples that follow, we will see that n of E and n of S are sometimes found by counting combinations. And I'd like to review this do now problem to show you how. Here, there's a little bit of overlap between permutations and combinations, which we will explore now. Remember this problem? 2 cards are drawn from a standard deck of 52 without replacement. What is the probability of drawing 2 aces? Well, an ace and then an ace. Well, we considered the probability that the first card is an ace times the probability that the second card is an ace, and the probability that the first card is an ace is 4 out of 52. The probability that the second card is an ace, once the first card is drawn, would be out of 51, but then there are 3 aces left. So the answer would be 4 times 3 over 52 times 51, which in a previous video we discussed was the 4p2, the number of ways to arrange 2 aces from 4, divided by 52p2, the number of ways to arrange 2 cards from 52. However, this problem can also be solved using combinations as follows. Okay, so this is method 1. So we could think of the following. We determine the number of ways to accomplish the desired combination. That is, the number of ways to select 2 aces from 4 aces. So, the number of ways to select 2 aces from 4 would be 4 choose 2. Because here order doesn't matter. And the total number of possible outcomes would be the number of ways we could select any 2 cards from 52. So the probability that we select 2 aces from 4 can be the 4c2 divided by 52c2. Now let's compute that and see what we get. Well, 4c2 is 4p2 divided by 2 factorial, and 52c2 is 52p2 divided by 2 factorial. These would cancel if we multiply the top and bottom by 2 factorial over 2 factorial. So this is equivalent to 4p2 over 52p2, which is exactly what we obtained above. 4 times 3 over 52 times 51. So here is an example where we can consider either permutations or combinations. Which way do you like better? Well, personally, I like this one the best. It makes the most sense to me. But again, it's nice to see how permutations and combinations overlap in this sense. But remember, with permutations, order matters. So let's write that down. There's order, and a good word is arrange. Whereas combination, we'll look at it when order doesn't matter. And the words to look for are committees or select. So it's very interesting to see that when we pick two cards from a standard deck without replacement, the order does matter in a sense if we consider the probability that the first is an ace and the second is an ace. But then selecting two aces from four, we don't think of the order mattering. And selecting two cards from 52, we don't think that that matters either. So let's take a look at another problem. For some probability problems concerning arrangements in which order is not important, the most appropriate method of solution involves combinations, like the next one. Now, in the next problem, let's take a look at this. In a group of 6 boys and 4 girls, what is the probability of selecting at random from that group a committee? All right, so let's look at these key words. Selecting and committee. Cries out combinations. So we have 6 boys and 4 girls. What is the probability of selecting at random from that group a committee that consists of 2 boys and 1 girl? So let's take it step by step. So let's consider the number of ways of selecting 2 boys from 6 boys. And that would be 6C2. And the number of ways of selecting 1 girl from the 4 girls. Well, that's just 4C1. And since we want to select both of them, we use the counting principle. And we multiply them because we want to select 2 boys and 1 girl. So we multiply, and the answer is 6C2 times 4C1. And the total number of ways to select 3 people from the group of 10 would be 10C3. Because notice that these are the total number of outcomes that are possible in forming a 3-person committee from 6 boys and 4 girls. So the probability that there'll be 2 boys and 1 girl would be the number of ways to select 2 boys and 1 girl, which is 6C2 times 4C1, divided by the total possible committees of 3, which would be 10C3. And if we compute this, we get 15 times 4 divided by 120. I'll leave this up to you, and the answer is 1/2. So this is our answer. Okay, let's look at part B. In part B, we want to form a committee of 5 people that contain all girls. Well, let's think about that. There are only 4 girls in the group. So it's impossible to form a committee of 5 girls. So in that case, the answer to the probability is 0. Okay. Now, how about the probability of 7 people that contains a boy? All right, let's think about that one carefully. Well, let's see. Since the number of members of the committee is 7, and 7 is greater then the total number of girls in the group, which is 4, there must always be a boy on that committee. Okay, so let's think about that again. We have 4 girls. So if there has to be one boy in the committee from the 4 girls, and we want to form a 7-person committee, so here we'll say that the total number of girls, there are 4 girls, and if we pick the 4 girls, there must always be a boy on the committee. There has to be, because even if we pick all 4 girls, there has to be at least one boy in a 7-person committee. So the probability that 7-person committee has a boy would be 1. That's absolutely certain. All right, let's try another. All right, now let's take a look at 3. A candy dish has 10 candies, and these candies are wrapped in foil. And 3 of these candies are covered with a red foil, and 7 of these candies are covered with a green foil. 2 candies are chosen at random. So look at the words, chosen. That means we're going to select. The order does not matter. Find the probability, A, that both will have the same colored foil, and B, each will be covered with different. So the probability that both will have the same foil, and that means that they're both red or both green. So probability, oh, again, I have the wrong pencil. Probability that they're both red, or the probability that they're both green. We add these 2 probabilities. We have that or. Okay. Now, the number of ways that we could get 2 red foiled candies would be 3 choose 2. And the number of ways that we could get 2 green foiled candies would be 7 choose 2. Again, there's 7 green, and we're going to choose 2. Here we have 3 red, and we're going to choose 2. Because we're considering probabilities, we have to consider, and how many ways can we select 2 candies from the total bowl? And altogether, they're 10 candies. So when we add these 2, we get 3C2 plus 7C2 over 10C2. 3C2 is the same as 3C1, which is 3. 7C2 comes out to be 21, and 10C2 equals 45. So the answer is 8 over 15 if we simplify the fraction. And I don't expect that on your paper. I'm happy with this answer here. So here, if we want them to be of different color, then consider that the probability that they are the same color plus the probability that they're different colors would equal 1. So in this case, it's easier to look at the complementary event. That is to say, the probability that they're different colors would equal 1 minus the answer above. So that would be 1 minus 8/15, which gives us 7/15. Another way to do the problem, okay, this is one way. Another way to do this problem, though, is to consider this. If we want, okay, let me just put a little star here. So if we want the two candies to be chosen at random and they have different foil and order doesn't matter, then we're considering the probability of choosing one red and one green. Now that would be choosing one red from the 3 and one green from the 7 divided by the total number of ways of choosing two candies from 10. And when we work this out, we get 3 times 7 divided by 45, and you see that the answer is 7/15, since the 3 goes into the 45 15 times. And that could be a little confusing because here order does not matter. But if we go back to permutations and redo this problem, so again, the way we did it before, the probability that we have different colors when we pick two candies and order matters, if we consider order matters, I would consider the probability of the first red and the second green, or the probability of the first green, second red. So we have 3/10 times 7/9 plus 7/10 times 3/9. And when we work that out, we get 7/15. So we see this, there's a marriage between permutation and combinations, depending on how we look at it. All right. And the last problem with this candy problem that I wanted to do is that, and I'll call this part C, if 5 candies are chosen from the dish, what is the probability that at least 3 will be covered with green? Okay. All right. I'd like you to pause the video and do this any way you like. Whether it be combinations or permutations, try it. But this word at least 3, keep in mind, this means that we want the probability that 3 out of the 5 are green foiled. The probability that 4 out of the 5 are green foiled. Or the probability that all of them are green foiled. And because any one of these are possible, we add these probabilities. So do this any way you'd like. And I'll continue on the next page. But pause the video. Okay, so I wrote out the probabilities here, but when we consider this as a combination, we have to consider how many green and how many reds we have, since we're picking 5 candies. So if we pick 3 green, then that means we're picking 2 red. Oh, let me have fun with my markers here. And if we pick 4 green, we're going to pick 1 red. And if we pick 5 green, we're going to pick 0 red. Okay, so let's look at the numerators. Well, the denominator of the probability is easy, because since we're picking 5 candies from a total of 10, okay, now let's look at these. So to pick 3 green from the 7, we have 7C3. To pick 4 green, that would be 7C4. And to pick 5 green, that would be 7C5. But don't forget that we're also picking red as well. So to pick 2 red from the 3, that's 3C2. 1 red would be 3C1. And 0 red would be 3C0. And again, we multiply by the counting principle because we're picking them both at the same time. And. So this is one way to do it. And if we figure this out, let's do this quickly. So again, these are easy to figure out. This is 3, and this is 3, and this is 1. Remember, NC0 is 1. So all we have to do is figure out 7C3, 7C4, and 7C5, and divide that by 10C5. But doing the work, and remember, 7C3 is 7P3 over 3 factorial. So that's 7 times 6 times 5 over 3 times 2 times 1. So again, we see that going through the factors, the 3 times 2 is 6, and this should give us 35. So going through the math, and I'll leave that up to you, the numerators all come out to be 105, and 10C5 is 252. So our answer in unsimplified form would be 231 over 252, which simplifies to 11 over 12. Doing this problem using permutations is very difficult. Let me show you why. If we were going to consider the number of ways to have 3 green and 2 red, using the counting principle with just like we do with permutations, well, the number of ways to pick 3 green, well, we have 7 green, so it would be 7 times 6 times 5, that's for the 3 green, and the 2 red would be just 3 times 2. But again, because order does not matter, just like we rearrange the letters in a word where there's repetition, we divide this by 3 factorial times 2 factorial. And if you look at this very carefully, this is equivalent to 7C3 times 3C2. Okay, this whole expression. So it's really worth our while in a problem like this to use just combinations, because just this case requires a lot of work. And we have to divide by the number of ways of choosing 5 candies from 10 anyhow. So that's a combination. So I would definitely do this problem using combinations. So let's end this session with this last problem. Suppose we have 4 red marbles in a jar and 6 blue marbles in the same jar, and we would want to find the probability that there are at most 4 blue marbles if we select 6 marbles from this jar. Okay, so try this by yourself. Pause. Oh, and let's just review what we mean when we say at most. That means that we have either most 4 blue. So if we could have 4 blue, we could have 3 blue, we could have 2 blue, or we could have 1 blue, or 0 blue. Shouldn't forget that. So at most 4 would represent these probabilities. And because any one of these would work, we have that magical word or, and we add. So try this by yourself using combinations and restart the video. Okay, so if we do this from the combination point of view, we have to consider that we have 6 marbles altogether, and if we want a certain number of blue marbles, then we must have a certain number of 6 marbles. So we have to find the probability of 0 blue and 6 red, plus the probability of 1 blue and 5 red, plus the probability of 2 blue and 4 red, plus the probability of 3 blue and 3 red, and then finally the probability of 4 blue and 2 red. So that would give us at most 4 blue. Now, let's consider the denominators. Because we're selecting 6 marbles from 10, each of these denominators would be 10C6. 10C6 plus 10C6. These are the total number of ways to select 6 marbles from 10. Okay, but to select 0 marbles from the 6, 0 blue marbles from the 6, that would be 6Z0. Actually, I'm going to put this in blue. 6Z0. This one would be 6C1. This one would be 6C2. This one would be 6C3. And I think I forgot one. Oh, let me just correct it. All right. So with a little bit of editing, so to pick 0 from the 6 blue is 6C0. 1 from the 6 blue is 6C1. 2, 6C2. 3, 6C3. And 4, 6C4. But we multiply because we're picking red as well. We have something interesting here. We have 4 red marbles and we're going to pick 6. That's impossible. So this is 0. We still have 4 red marbles. There's no way we could get 5 red marbles. So that's a 0. To pick 4 red marbles from 4 would be 4C4. Just pick all of them, which is one way. 4C4 is 1. To pick 3 red marbles from the 4 would be 4C3. And finally, 2 red marbles from the 4 would be 4C2. So these two give us 0, the first two probabilities, 0 and 0. Well, let me just put that in black. But we would have to work out the rest. So let's do that. All right, so we'll do this on the side. So I computed the combinations on the side here, 6C2, 6C3, 6C4, and 4C2. So again, remember, this is 6P2, so that's 6 times 5 over 2 factorial. This one is 6 times 5 times 4 over 3 factorial. And 6C4 is 6C2, so that's the same answer as 15. And 4C2 is 4 times 3 over 2 factorial, which gives us 6. Now, let's put it all together. So the numerator for this fraction would be 15 times 1 over some number, which I didn't compute yet. 6C3 is 20 times, now 4C3 is 4C1, which is 4, over the same number. And then 6C4 is 15, and 4C2 is 6 over some number. Now we have to figure out 10C6, so let's do that. 10C6 is the same as 10C4, which is easier. So that's 10 times 9 times 8 times 7 over 4 times 3 times 2 times 1. The 4 and the 2's divide through. Well, let me just do that quickly for you. So this 4 and 2 divides through the 8, and 3 goes into the 9 3 times. So it looks like it's 210. If I did this arithmetic correctly, I hope. Okay. Wait, is that right? 3? No, it's 21, not 210. How did I get 210? I don't know why I added that 0. Okay, so it's 21. Oh no, it is 210 because it's 3 times 7 times 10. Yes, that's correct. Okay, so this is all under a common denominator of 210. So when we add 15 and 80 and 15 times 6, which I believe is 90, over 210, we get 185 over 210. And that would be my probability. All right. Now, I'm wondering if there's another way to do this problem. And I think there is. If we take a look at the complementary event, let's just finish this off. We could consider it as 1 minus the probability of having exactly 5 blue and exactly 6 blue. But if we have exactly 5 blue and 6 blue, and we're picking 4 marbles, then in this case we have 1 red, and here we have 0 red. So let's see if we get the same answer. So let's use combinations again. So if we use combinations here, to pick 5 blue out of the 6 would be 6C5. And to pick 6 blue out of the 6 would be 6C6. And note that's 1. Just pick them all. Now, here we have 1 red. So the number of ways to select 1 red from 4 would be 4C1. And the number of ways to select no reds from 4 would be 4C0, which again is 1. Don't select a red. And each of these would be divided by 10C6 because we are picking 6 marbles from the 10. Now let's work these out. This shouldn't be too bad. So remember that 6C5 is the same as 6C1, and that answer is 6. And the same way, 6C6 is equal to 1, and 4C0 is equal to 1 as well. So when we substitute this, we get 1 minus 24 plus 1 divided by 210. So that's 1 minus 25 over 210. And using the math, we should get 185 over 210, which is exactly what we obtained the other way. Okay, that takes care of our lesson on probability with combinations. And again, look for those magical words, select and choose, where order doesn't matter. Have a wonderful day.